Okay, the first thing we want to finish is our discussion of flux limiter from last lecture. So from last lecture, we studied the concept of limiter, which is a mechanism of introducing non-linearity into a numerical scheme, even for solving linear equations. Okay, it is introducing non-linearity in the stage of reconstruction. So remember, in finite volume, we are having a piecewise constant approximation, or in other words, it is an approximation that stores only the volume averages. And reconstruction is trying to take these volume averages and extrapolate to what is supposed to be on the interfaces. The flux limiter says that the reconstruction, the extrapolation, is appropriate only in regions where the solution is continuous and smooth. And extrapolation should be turned off at what locations? Extremus, when the local solution is at the maximum or the minimum. So when the solution here is higher than both of its neighbors or lower than both of its neighbors, the extrapolation should be turned off. That is why we introduce the limiter phi as a function of R, where R is the ratio between the two neighboring differences. Okay, it's a ratio between ui plus 1 minus ui and ui minus ui minus 1. If the ratio is equal to 1, we know locally it is a very smooth region. And if the ratio is negative, we know it is either a local extrema, local minimum, or local maximum. So the phi controls whether we should do a extrapolation or we should stick with the piecewise constant approximation. Okay, and during the last lecture, we started working on the MATLAB demo. Last time we started working on the MATLAB code. That's called Steele-Burgers DDT, and we started adding limiter in the reconstruction. And after last lecture, there was one of the students pointed out a bug in my code. So who did that? I don't remember. Okay, you did that. Thank you for that. So there is a bug in the code. The ratio shouldn't be constructed as, I think, shouldn't be constructed as I plus 2 minus I plus 1 divided by I plus 1 minus ui. It should be I plus 1 minus ui divided by I minus 1, right? This is the correct ratio for me to extrapolate from I to I plus half. All right. I think, is this correct though? I'm trying to construct the interface at the right hand side. Okay, and I think this is correct, right? Because I'm trying to reconstruct the solution at the left hand side of the cell I plus 1. So the ratio is I plus 1 minus I divided by I plus 2 minus I plus 1. All right. Okay, good. So let's test this out. So again, I'm going to draw a function with 128 nodes. And from last lecture, we observed a problem when we have a discontinuity like that. So we're going to draw again a function like that. And I still need my x and xx. Okay, just for plotting purposes. So here I'm going to do a for loop that is exactly the same as what we did before. And let's run with this code. Okay, I need to define a dt and go. Here we go. So with the limiter on, we see that we no longer have created a new extrema. So the solution never dips below this this minimum of the original initial condition, and it never exceeds like the maximum of the initial condition. And the solution is still going to be a second order accuracy. Okay, suppose we want to change to a different limiter. What do we do? What should we do if we just change to a different limiter? We only need to change this function, right? For example, this is the min mod limiter, right? So if I change it to, so let me just comment it out. What is it? Nope. If I comment this, okay, and I'm going to do a different limiter. Okay. So I always have, if r is less or equal to 0, my phi has to be equal to 0. That's a commonality between all permissible limiters, right? But the other case can be different. So for example, if I want to do a Van Leer limiter, the formula would be equal to 2 times r divided by r plus 1, right? I have phi equal to that. Okay, so let me make sure what happens when r is either infinity or not a number. So if r is infinity or not a number, we don't want the phi to be infinity or not a number, right? So this formula cannot really be used like that. Instead, I need to else if is finite r. So is finite, is that a appropriate function? Yes. Okay. So if it's finite, I'm going to do this. And if r is either infinity or not a number, this function is finite, is going to return, if I do this, it'll return 0, or infinity, it'll return 0. So in that case, what should I do? Anybody? 0? Okay, if it's 0, I should return 1. If it's infinity, I should return 2. That's a good intuition, I think, from the fact if it is equal to, if it is not a number, both sides are 0, I should stick to the behavior of extrapolation. And actually, in that case, it doesn't matter at all what value of phi is, because the slope is going to be 0 anyway. So no matter what phi is, piecewise constant or extrapolation is the same thing. So as long as phi is a number, I'm fine. The other case, if phi is infinity, that means one side of the slope is equal to something, the other side of the slope is equal to 0. And you're going to see, again, the phi is going to be multiplied with 0, so it doesn't matter. Anyway, we can set phi equal to 2 as what you suggested. All right. Okay, so once that is fine, I can perform another simulation. So let me just let me draw another function again. All right. Now again, we see the behavior of total variation diminishing in the solution. So we are not creating any new extremas or any new maximum or minimum. All right. So any questions on how the limiter is constructed? And in this case, you're going to see the shockwaves are going to be a little bit sharper than in the previous case, because I'm doing a more aggressive reconstruction. The slope I reconstructed is going to be a little bit higher than the mean mode case. Okay. All right. Any questions on limiters or on finite volume in general before we go into finite element? Yes.